Hello, welcome back to this tutorial on system dynamics modeling and STELLA software. This is the 7th video in this tutorial and the second video in module 2 where we are building our own models in STELLA. So if you're just joining us, I recommend going back and watching the last 6 videos so that you can get a background on system dynamics modeling and also the simple population model that we will be building off of today. So as a reminder, the model that we built in the last video was a simple population model built off of this causal loop diagram. As you remember, we have one stock, population, and two ways for that stock to change, births and deaths. Births increase the population and deaths decrease the population. And then we have no other important parameters, and so we have no converters in that model. Today, we will be building off of this model and making it a little bit more complicated to represent some more processes within this system. So here is the more complicated version of our population model that has the same base. We have our population and births and deaths. But in this model, population is also dependent on a series of other processes based on the number of resources available for each person. So to get started, let's go ahead and find all of our stocks, flows, and converters. Just like the last model, this model will have only one stock, population. We are interested in the number of individuals in our population and how that population changes over time. Also similar to the last model, there are only two flows in and out of our stock, births and deaths. However, there are some new parameters in this model. So we can see that population size is going to negatively decrease resources per person. The more resources each person has, the greater their life expectancy. The greater the life expectancy, the smaller the desired family size. And the smaller the desired family size, the less the birth rate is. So these are some interacting parameters that complicate the picture a little bit and add some more important processes within this system. Now we're going to move over to STELLA. We'll be working directly with our last simple population model and adding on to it to include these other important processes. All right, I'm using a little split screen here so that we can see the causal loop diagram over here on the right while we make a model on our left. So like I said, we'll be working directly off of our simple population model, so you can just go ahead and open that file and edit it directly from there. We're going to keep this graph up here too, so that we can watch population over time, because that is still the stock that we're interested in. Okay, so we have our base model here with our two flows, births and deaths, that are dependent on both population and birth and death rate, respectively. So let's go ahead and start adding new parameters. So right here, resources per person, we can tell by this little negative sign that it is negatively impacted by population, or inversely correlated with population. This means that as population increases, resources per person is going to decrease. So what that says to me is that it is dependent on population. So let's make a converter and call it resources per person. And we know that population affects resources per person. And we can also make a converter for resources, because resources per person obviously depends on how many resources are available. So we're going to make this a constant, and we'll set it at 10,000 resources, just a vague placeholder. And then resources per person is going to be resources divided by population. All right. Then we can see that resources per person is positively correlated with life expectancy. So let's make another converter. Call that life expectancy. And we know that it is affected by the number of resources per person. So we can draw a connector between those two. So if life expectancy is a function of resources per person, we can think about that as a certain number of years gained for each resource. So we'll make another converter called years per resource, and this symbolizes the number of years that a person would gain for each extra resource that they have. We'll go ahead and say that's 5, given that we have 10,000 resources and 1,000 people. That leaves about 10 resources per person, setting our average life expectancy to 50. So we can use a connector and draw those, and draw between those. And then we can set life expectancy to resources per person times years per resource, because as I said, it is positively correlated to resources per person. So what this will do is increase life expectancy depending on how many resources are available per person. Okay. The next part of our causal loop diagram is that life expectancy negatively impacts desired family size. The two are negatively correlated or inversely correlated. And this is just to show that as life expectancy increases, people are more likely to be educated and have careers that make them less likely to have a larger family. So let's make another converter and say, call it desired family size. We know that it is impacted by life expectancy, and we know that the two are inversely correlated, so we can go ahead and say that desired family size is equal to 1 divided by life expectancy. So that will ensure that those two variables are negatively correlated. And then finally, we need to connect desired family size to birth per person or birth rate. And to do this, we will draw another connector between desired family size and birth rate. And then we can say that birth rate, instead of a constant, we can say that birth rate is equal to desired family size divided by 2, because each family requires 2 parents. So now let's take a look at our new model. And first, let's look at our old graph where we had where our system was in equilibrium. So our births were equal to our deaths, and therefore our stock or population stayed the same over time. And now let's run our new model and see how that trajectory changes. So now we see an exponential decay in our population, and that's because as population increases, there's going to be fewer resources. And so to maximize the number of resources per person, the population gets smaller and smaller. As the resources per person increases, so does life expectancy, and then family size decreases and decreases birth rate. As you can see, STELLA will highlight positive and negative feedbacks and the strength of those feedbacks through these blue and red arrows. And if you ever want to get rid of that, you can just unclick calculate loop dominance information down here at the bottom. And then when you run the model, those feedback loops will not show up. So this is a great example of how including new processes in your model can completely change your model behavior and how it simulates your system behavior. And depending on which questions you want to ask, you might want to include different processes in your model. For example, if you're especially interested in how resources are divided among the population, you might want to include that in your model. And again, we can look at our converters and say, okay, if we had more resources, how might that change the population? And again, we can change these converters to see how more resources might change the population trajectory, or how fewer resources might change. Whoop. So yeah, we can see that population is going to decrease even if there are fewer resources, to the point where we see a large change in population behavior. Thanks for watching, and join me in my next video where we'll talk about how to optimize and calibrate models to real-world data.